Hi, and welcome to this episode of Science Speedrun, in which we're going to find out whether wintertime changes the incidence of depression. So in this week's episode of Science Speedrun, we will read and try to reproduce a paper by Hansen et al., who took Danish hospital data, hospital register data, from a number of years and tested whether the incidence of unipolar depression, so MDD, major depression, and bipolar depression, right after the time changes to summertime or the time changes to wintertime. And what they find is that when there's a time change to wintertime, there is actually a 10% increase in the incidence of unipolar depression, of MDD. So that's what we will focus on. Now, the way they study this is with a variant of what's called a regression discontinuity design. So let's head over to the drawing board and let's sketch out what a regression discontinuity design actually is. All right, so I'm going to sketch for you the basics of a regression discontinuity design, where I've already printed a little set of axes. The x-axis, which is usually time in a regression discontinuity design. So time before, 0 is time before the discontinuity occurs, and time after discontinuity. And then y is the axis of the outcome. So in our case, or in Hansen et al.'s case, that's the logarithm of the incidence of depression. And so for regression discontinuity, there's observations, right? So at the times before and after the event occurs, there's observations. And then the discontinuity is our exposure in our study. And so there is data before and data after, and the effect estimate in a regression discontinuity study basically boils down to an estimate of the outcome of interest before and after the discontinuity, where the effect estimate is the difference between those two. But there is subtle complications here that we should really briefly discuss. So one complication is actually that you don't really know how to model the time right around the discontinuity. So you can imagine, for example, there is some sort of series of data, and then there's an effect, but the effect wanes. We don't really know how quickly it wanes. And so if we were to estimate just the level of the outcome before and after the change in this time window we're looking at, you'd estimate something like this, because that's the mean before and the mean after, and you'd think the effect was this, where in reality the effect seems to wane really quickly. And so yes, true effect of the discontinuity, or whatever occurs or happens at the discontinuity, is actually this effect, which is bigger. Now, this is a very transparent example. In reality, this might be more subtle, and then it's harder to sort of really make sure you model that sort of, decay or whatever happens to the effect after discontinuity properly. And so an added complication to the paper we're actually discussing is that it's a time series, right? So it's actually the incidence of depression in a certain week may actually influence the incidence of depression in the week after. And if something really big occurs in this week, then it may still have a sort of a transparent, smaller effect this week. Then through years, so not weeks, but through years, there's also like maybe an increase in depression or a decrease. And those things we should also model. And that's what actually the authors do. And then to specifically deal with what happens after the discontinuity, they actually model like an immediate increase in the incidence, and then they say, well, but we'll allow that to slowly sort of decay with a couple of percent or a fixed number of percent per week, and they estimate that decay and the instantaneous sort of increase in incidence. Okay, well, that was my poorly drawn sketches to try and explain to you regression discontinuity. Let's head back over to the computer and we'll go and fit some of these models. Okay, so here it is, the paper by Hansen et al., in which they check out whether changing to daylight savings time or back from daylight savings times in the summer to the winter time actually has an influence on MDD, so unipolar depression, or bipolar depression. And they actually find an effect for going to wintertime and for unipolar depression. So that's what we'll focus on in replicating their results. And so what we'll do today is we'll first quickly describe the details of their paper, then we'll download their data, we'll go into R, and in R we will actually try to reproduce their table 2, which contains the effect estimate, right? And so what we should know is that the data for this paper is weekly incidence of depression in Denmark between 1995 and 2012. So that's every week there's an incidence, number of people that get depressed over the number of people that could potentially get depressed, I guess. And that's the time series we model. And we don't model the incidence directly, but we model the logarithm of the incidence so that our effect estimate actually becomes the percent change in incidence, right? And so one thing to note is this is a special kind of regression discontinuity because there's actually a discontinuity every year. Every year we go to wintertime, every year this reoccurs, and every year so the incidence can change. But it also means that we will have to model the dependence between the incidence in one week and the next. So imagine there's a very busy week in the hospital, then that will have an influence on the incidence next week just because there may be no beds available. So those are things we need to take into account. Also, there may just be a trend of the incidence of depression going up throughout the years in Denmark or down. I don't know. That's something we'll find out. So we'll need to use what's called a time series model. And that's what the authors actually do. They use a time series model in which there is a specific intervention every year, a sort of effect in the week that we go to wintertime. And that effect is estimated to be an effect in the first week. And then there is what's called a autoregression, which models that the effect then slowly decays after week 1. And so that's actually what they show in first figure, which is a simulation they do where they show, look, if you model the incidence with a time series, then you can model an additional external exogenous effect of something like, in their paper, going to daylight savings changes, right? So going from summer to winter time. And they model it as a moving average term, so it's like an effect in the week of the change, and that then decays over time, right? And so they do this model, they sort of explain how they categorize their data, and they show that there's actually a trend of increased depression incidence over the years, so that's something they need to take into account in their model. And then here they present their estimate, which is 11%, right, from going to standard time. So from summertime to standard time on unipolar depression, there's an instantaneous effect for that week, that first week, of 11% increase in incidence from their model. And then that actually decays in a number of weeks with that decay parameter we just discussed. And so they say, well, the incidence increases like 10% in the first week, and it decays all the way up to 10 weeks after when it's near its baseline again. Okay, now they made our job fairly easy because if you go to the bottom of the article, you'll see 3 or 4 links to supplemental information. Appendix 2 is actually the data, which is, I assume through some process at the journal, right, presented as a PDF, which is super annoying, but you can copy paste it into a text file and it will be something you can read into your R. And then there's also the R script, which is actually Appendix 3, right? And so I've downloaded those, I've gone ahead and copy pasted stuff from that PDF into a text file, and now we're going to read it into R and try to reproduce the results. So this is the data in R. Like we're in R Studio now. This is sort of the data provided by the authors. This is a little script I wrote to read that data, and I can go ahead and run that, and then the data set will be introduced into R. And then we can actually just follow their script, right? Load to library, stay loaded, and we'll go ahead and run that script up to when we make that table with the result. Right, and so that's actually right here, I think. Yeah, that's right here. And this is the table 2, with the result. That's basically the headline result of their paper. That going to wintertime has a 10% or 11% effect on the incidence of unipolar depression. Let's go ahead and run it. Now, some of the models will take a second to run, most of them will run instantaneously. And if things went okay, then there is this out file. So this is actually just their models are ran here, right? The models are on depression and bipolar depression. And then the results of those models are presented in this table. And here's the table. Let's go ahead and open it in a browser. And actually, if we compare this to the PDF we just had, right? Where is it? Not there. Let's just compare it to the paper then. Let's open. This is the table I just made using their data that I found accompanying their manuscript. And if we put it side by side with the table they present on the website in the journal version, then you'll see that the only difference is rounding. These are exactly the same results. And that's super, super awesome. Like 10 out of 10 in terms of reproducibility for these authors. This took me no more than 2 hours to figure out when I first looked at the data. And the fit's identical, the AIC, sort of some of the fit metrics associated with the model are identical, and it's really a genuinely really great job. Here it is, 10.8%, which is a rounded version of that 11% increase in incidence in MDD when wintertime goes into effect. But, that's us reproducing their results. There are some questions I had when I fit this data and when I read the paper, and one of them was like, look, you're imposing this model where there's an instantaneous change that then decays, but what if it takes a few weeks for people to get to where they are diagnosed, right? People aren't diagnosed instantaneously when they get depressed. There's like wait lists and getting an appointment and going to a doctor that can easily take more than a week. So one thing I want to test is like, what if we don't do one of these effects that decays, but just do an effect of like the risk of the incidence of diagnoses a couple of weeks after and before the time change. And the second thing I found sort of suboptimal maybe, or I may have done differently myself, is that they model the entire year. But this also means that things that happen around Christmas or in January that are still going to potentially influence the estimation, which is kind of weird. We're really interested in what happens right before and right after the change from summer to winter time and the other change, but that one didn't yield a very interesting result. So we're going to focus on the one where we go from summer to winter time. And so I made a script with robustness checks where I take their data and which they provide, so the average incidence per week for those 900 something weeks, and I do my own analyses. And so what I do is I make a lag variable, which just indicates whether a data point is between 0 and 5 weeks after the time change or between -1 and -5 weeks before the time change. And I make a time series out of that lag variable. Let's go ahead and do that. Run the script until that point. And then first I'm just going to visualize the incidence of depression right before and right after the time change goes into effect. And that looks something like this. And as you can see, this is the incidence across the many years in their data set. I think it's 17 years. So it'd be 17 incidences for each week. This is where the time goes from summer to winter time. And as you can see, like this is a nonlinear Loess curve. So it will just go and try to approximate the mean at that point in time. Well, and it goes up a bit right after going from summer to winter time. And then it decays again. But it decays like after a few weeks already. So that's interesting. And so let's also remove the observations that aren't in this window from the depression variable and make a new depression variable that's called depression 2. Right? And then we'll fit the same time series model, but we'll restrict the data to these 11 weeks. And first I'll test an exposure that is this the incidence after or before the time change? So just a binary exposure, no fancy model with decay. And if I run that model, I actually get an estimate. And the estimate is 0.05, and it's 5% increase in incidence in the 5 weeks after compared to the 5 weeks before the wintertime goes into effect, right? Allowing for a time series model over that period. And that period's repeated for the 17 years that are in the data. Okay. Now, if you, unlike me, think, no, their model of a peak and then a decade, that is proper. But yeah, maybe, Michelle, you're right about this sort of window of time around the change to wintertime. Then you could run this model. But you can also run your own model. These scripts are going to be available on my website, where there's a blog post taking you step by step through the entire process. And you can run your own alternate model if you wish. If you disagree with me or the authors, feel free. And so running the model where there's a reduced time window, but there's still their model, you get like an estimate of 7% change going into wintertime. I checked, the other estimates are also very stable across these models. And in general, I don't think this invalidates the results in any way. These are choices I made. They made different choices. These aren't necessarily wrong or right choices. And also they don't necessarily change the result dramatically. So there's still an incidence, we still estimate an incidence change. And so, yeah, their results reproduce, their results are robust. And I guess we'll come back to you in a second and get to some conclusions, get to some suggestions for replication.
Okay, time to discuss what we were able to learn from the Hansen et al. Study and trying to reproduce it. Now, I want to start with a big compliment to the authors, because basically making the data available, making the code available, that's like the key to reproducibility. Yes, the data was in a PDF, but I'm going to assume that may have been a journal demanded format. And it was easy enough to read into R. It was easy enough to replicate their tables, their figures, those aren't in the video, but I've tried to reproduce all the other results. And as far as I could see, things were at the estimates they presented in the paper or within rounding. So this is really 10 out of 10 in terms of reproducibility. Then when we're comfortable that we're sure that the paper presents a real effect, the question that arises obviously is, what is that effect, right? And so things you could think about for a replication where you go to new data to see if the effect holds is to go to other nations that have weekly incidence data or that can generate weekly incidence data. I'm pretty sure you could generate those based on NHS data in England or in Sweden, in Norway, where they also have really big medical registers. And you could try and replicate these results. But beyond these results that are the incidence of depression, one question I had in my own mind was, are people getting more depressed, or is the medical system responding in some different way? They probably are strained on these days and weeks after the daylight savings, because there's evidence from other authors that there's more car crashes, and in the daylight savings change to summertime, there's actually more cardiac arrests. So there's other things changing at the same time. So are we seeing a change of the individual or a change of the healthcare system? And I think maybe a mix of both. Who knows? That's something you could go and find out. And one way to find out would obviously be to take individual level data of other observational studies and go and test whether symptoms of depression actually respond to daylight saving study. And in a future video, that's exactly what we'll do. We'll go try and replicate this. Until then, thank you for watching. This is Michel, and this was Michel's Science Speedrun.